Today we are on page 8 of the Chapter 5 AP Notes on gases, and we're going to be talking about collecting a gas over water. As you remember in the class demonstration, the way to collect a gas by itself is to have an inverted container filled with water, and then your source of gas is going to come in and bubble into the water, pushing the water out of the container, and then being left with the gas inside the container. The only thing you have to understand is that you also have water vapor in this container as well, because the water evaporates into the container. And so any pressure in this container is going to be the sum of the pressure of the oxygen, in this case, and the water vapor. The interesting thing is that both of these are going to add up to the room pressure as long as you make the level of this water level with this water. So in this diagram, it would not be accurate at this moment. You would have to push the jar, the inverted jar, underneath the surface of this water until these two levels were the same. And when these two levels are the same, the pressure inside is the same as the pressure outside. So the room will be the sum, the room pressure will be the sum of the oxygen and the water vapor together. So in this problem, we have oxygen gas produced according to the unbalanced equation below, collected over water, the vapor pressure of water 27 degrees. You'd have to look that up on a chart, which I'll show you in a minute. The first thing you need to do is balance the equation. So this is going to be a 2 and a 2 and a 3. Now what they're doing is they're giving you a whole bunch of information. They're saying how many grams of potassium chlorate, so that's this, grams of this, must be decomposed in order to produce this much oxygen. If you look at all these pieces of information, they're giving you information about Pivnert. So here's the volume, here's the temperature, here is the pressure, but this is the pressure of the room. So you have to be careful. This is the room pressure, not the oxygen's pressure by itself. So you have to picture in your mind what's happening. Here is the KClO3, potassium chlorate. When you heat it up, it actually decomposes into potassium chloride and oxygen. When it decomposes, the oxygen gas is going to go out of here through the tube and collect in this inverted jar. So now you have an inverted jar full of oxygen gas, but also water vapor. The question is, how much potassium chlorate did you have to decompose in order to get oxygen with all these conditions? So what we're going to have to do is we're going to have to use a Pivnert here, and we're going to do this Pivnert for the oxygen. I recommend whenever you do a Pivnert, write down the gas for which you're doing it so that you always remember this is oxygen information. So I need oxygen pressure, oxygen volume, oxygen moles, oxygen temperature. We already know that R is 0.0821 liter atmospheres per mole Kelvin. We know the temperature 27 degrees is going to be 300 Kelvin. We are actually going to use the volume here, but in the right unit, so this is 0.8 liters. And now we're going to look for the right pressure here. So this pressure is 1.2. This is the room. What you have to understand is that you need to take the room, which is the total pressure, minus the vapor pressure of water, and that's going to equal, the pressure of the oxygen. So the room pressure is 1.20 atmospheres. I'm going to work in atmospheres since that's the unit I need for Pivnert. Now I have to look up the vapor pressure of water right here. I have to look it up on a chart. And it's at 27 degrees. So we're going to go to the next page, 27.0 degrees. We're going to look at this column right here where it tells you the temperature is 27 of water. And then you're going to look up here for the decimal point, so it's 0.0. So you're going to look up 0.0. And we're going to follow that down, and we're going to get 26.739. But be careful, because the unit of this is in torr, or millimeters of mercury. Okay? So you have to understand this is in millimeters of mercury. You might even want to, oh, here it is. You could just circle that right there. Okay? It's in millimeters of mercury. So our number is 26.739. 26.739. So that's millimeters of mercury. 26.739 millimeters of mercury. Now what you're going to have to do is you're going to have to convert that into atmospheres in order to subtract it correctly. So we know that every 760 millimeters of mercury is 1 atmosphere. So you're going to take 26.739 divided by 760, and that gives you 0.0351. 0.0351. We'll go with 5 sig figs, 5, that's 1, 8, and 3. Now this is going to be far too many sig figs because we're not going to be able to use them all when we do subtraction. When you do this, you're going to have 0.035183, but with our sig fig rules, remember it's line them up, so you're actually going to have to cut off your answer right there. You can see that the answer, that pressure is not going to change significantly, but of course there will be problems where it'll make more of a difference. So we're going to take 1.2 minus that number. We're going to get 1.1648. Let's see if I'm doing this right. 16482 or 17. Okay, I see what happened here. 17. Anyway, the sig figs are not going to matter. 1.164817. Okay, but you got to cut it off here. This is not going to round that up, so the answer is going to be 1.16 ATMs. So that number is going to be the pressure of just the oxygen. So let's just review one more time what we were doing there. We knew the pressure of the room. The room was 1.20. The room pressure is going to match the sum of the oxygen, in this case, in the jar, and the water vapor, as long as you take this jar and push it underneath the surface of the water until this level matches that level. So that was the room pressure, not the oxygen pressure. We had to get the oxygen by itself. So we take the room minus the water vapor to get the oxygen. How did we know the water vapor? We looked it up on the next page in the notes. Based on the fact that this was at 27 degrees, we knew the vapor pressure of water. We converted it to ATMs, and then we subtracted to get the ATMs for the pressure of the oxygen. Now we're simply going to solve for the moles of oxygen. So use your calculator to do that. 1.16 times 0.8 divided by 0.0821 divided by 300. That gives you the moles of 0.037. We'll do 3 sig figs. So it's 377. Just double check that one more time to make sure. Yep. Okay, so that's the moles of oxygen. So this is the moles of oxygen that you made, 0.0377. The question is, how many grams of potassium chlorate did you need? So the easiest thing to do would be to change this back into, well, actually, all right, the easiest thing would be to bridge in moles because it's the little bridge. So let's do that first. So this, moles. So you're going to take 0.0377 divided by 3 times 2, and you're going to get 0.0251. And now what you need to do is convert that into grams. So we add the molar mass of KClO3. Remember, we only use the formula, not the coefficient here. So we're going to take 39.1 plus 35.5 plus 48, which is 3 times oxygen, and that's 122.6. Okay, so then you would have to do a conversion. Every mole is 122.6 grams. So we multiply that by 0.0251, and we get 3.08. So the answer is 3.08 grams of KClO3 that was necessary to produce this condition of oxygen right here. So the quick recap, we did a PIVNERT. We had to get the right pressure of the oxygen by subtracting the vapor pressure of water. Once we did that, we put our moles here, we bridged over to the one we needed, and then converted to the unit that we were looking for. So the video is going to end, and you can do number 2 by yourself.